Welcome to the Deep Dive. Today we're exploring some really deep ideas, like what if the universe, deep down, prefers beauty over just, convenience? What if a mathematical equation dreamed up in someone's head could actually predict reality before we even had a hint of it experimentally?
It's a powerful thought.
Well, that's the world of Paul Dirac. He was this physicist who seemed to think exactly that way. Someone described his approach as listening for where symmetry whispers the rules before experiment shouts them.
That's a great way to put it.
So today, we're going deep into Dirac's incredible contributions. We want to see how his absolute belief in mathematical beauty, in underlying symmetry, led him to discover fundamental things about our universe.
Right.
And we'll also touch on how his work, even now, connects with some modern frameworks, like this idea of motion theory.
Exactly. Our mission really is to unpack Dirac's key insights, the ones that fundamentally shaped quantum mechanics and particle physics. We really want you to grasp how his focus on minimal invariance, finding the simplest, most robust symmetries, and this drive for max coherence per assumption, how that wasn't just like his personal taste.
It was more than aesthetics.
Oh, much more. It was a seriously powerful predictive tool. And yeah, we'll use this motion theory frame sometimes just as a lens.
Okay, so what's the quick version of that lens?
Think of reality as structured motion. Forces aren't poles, but more like gradients of sink pressure, a tendency for movements to align. And beauty, in this view, it's the shortest path to max coherence per assumption.
Yep.
It'll help us see the connections. By the end, you'll hopefully appreciate how one incredibly elegant equation from Dirac revealed spin, predicted antimatter, and basically wrote the grammar for quantum states.
All right, let's get into it. So set the stage for us. Early 20th century physics.
It was buzzing, right?
Oh, completely.
Yeah.
You had Schrödinger introducing matter waves, particles acting like waves.
Uh-huh.
And Einstein, of course, giving us relativity, changing everything we thought about space and time. Two huge pillars.
But separate.
Exactly.
Yeah.
And then comes Dirac. And somehow with this almost poetic insight, he writes down a single equation, just one line.
And it connects them.
It keeps both true. It elegantly combines relativity and quantum mechanics. It's just stunning.
What made it so special? The equation itself.
Well, first, it's linear. That sounds technical, but it's crucial. It means probabilities work out sensibly. They don't go negative or weird.
Right, that's important.
And it's Lorentz invariant, meaning it automatically respects Einstein's rules about spacetime symmetry that's built in.
Okay, so it's consistent with what was known.
Yes, but here's the kicker. It didn't just describe things we already knew. The equation forced new properties to exist. They weren't optional extras you bolt on. They had to be there.
Like what? What fell out?
Okay, this is where it gets truly amazing. First off, spin.
The intrinsic spin of the electron.
Exactly. Before Dirac, spin was something people observed added to the models, but didn't fully understand why it was there. Dirac's equation didn't just allow for spin, it demanded it. It demanded it. How?
It was, fundamentally unavoidable. A direct mathematical cost, you could say, of making a quantum description work with relativity's rules. It just popped out. A total revelation.
Wow.
Then there's the electron's magnetic moment. The equation predicted its value with incredible accuracy. Just boom.
And that matched experiments.
Very closely. Later, quantum electrodynamics, QED, refined that prediction even further, and the match with experiment is, well, legendary. One of the most precise agreements in all of science.
Okay, so predicting spin and the magnetic moment just from writing down a beautiful relativistic quantum equation. That's already huge. But he didn't stop there, did he?
Nope, he went further. And this is maybe the most mind-blowing prediction of all. Antimatter.
Right, not based on seeing anything weird in the lab first.
Not at all. It came purely from the math, from the symmetry of his equation. He saw these negative energy branches in the solutions and realized they implied pertinent particles. It was a theoretical necessity.
A mathematical consequence.
Precisely. And then, just a few years later, 1932, Carl Anderson's looking at cosmic rays.
And finds the positron.
And finds the positron, the electron's antipartner, exactly as Dirac's equation predicted. It was just a monumental validation of trusting the math, trusting the symmetry.
So it wasn't a lucky guess. It was baked into the structure of reality, revealed by the equation. His initial idea was that famous hole theory, right? this sea of negative energy.
That's right. He pictured this kind of infinite sea of filled negative energy states. And if one of those states was empty a hole, that hole would behave just like a particle with positive energy and opposite charge.
The positron.
Yep. Now that specific picture, the literal Dirac sea,
Yeah.
we don't really use that exact interpretation today. It's evolved.
But the core idea survived.
Absolutely. The fundamental takeaway is still rock solid. Antiparticles are not optional. They have to exist if quantum mechanics and relativity are both true.
So antimatter isn't just some weird exotic stuff.
Not at all. If we look at it through that motion theory lens, you can think of a fundamental particle's motion like a loop. And that loop can have two consistent orientations relative to the universe's background alignment.
Like spinning clockwise or counterclockwise, metaphorically.
Sort of. If you flip the global phase winding, how its internal quantum clock syncs up and flip its charge coupling, you get the antipartner. It's just the other valid way to exist.
So antimatter is phase-reversed coherence.
That's a great way to put it. It's not fundamentally different stuff, just the other side of the same coin required by the overall consistency.
And that helps explain things like pair production,
Okay.
where particles and antiparticles pop into existence.
Exactly. Why does that happen near Sphion fields like powerful lasers or near atomic nuclei? Because the local sink pressure, the tendency to align, is so intense there, it can actually nucleate both orientations, both the particle and antiparticle, out of the vacuum. While still obeying all the conservation laws, of course.
And this isn't just history. Dirac's ideas still echo.
Oh, definitely. We see modern echoes all the time. In material science, for instance. Things like graphene or topological insulators.
Those exotic quantum materials.
Right. Under the right conditions, electrons in those materials behave almost exactly like Dirac's original relativistic electrons. They act like massless Dirac fermions. It happens where the underlying structure, the alignment landscape, kind of straightens out. It linearizes. It's another confirmation of how deep and fundamental Dirac's mathematical structure really is.
That's fascinating. It makes antimatter feel much more integral, less like science fiction. Okay, so beyond the huge predictions, Dirac also gave physics new tools, right? A new language.
He absolutely did. A whole tool belt, really. That changed how physicists even talk about quantum mechanics. He gave it its terse composable grammar.
I mean, the bracket notation.
That's the big one, bracket notation. Those angle brackets and vertical bars. It seems simple now because it's everywhere, but it was revolutionary.
How so? What did it simplify?
It gives you this incredibly clean way to represent quantum states and operations. You can think of it like prepared state, the Ketre, goes through some process or measurement in the operator, and you check its overlap with a desired outcome state, the bra.
So it's like a shorthand for input state, process, probability of output state.
Pretty much. It streamlined everything, calculations, communication. It made quantum mechanics manageable.
And the motion theory angle on that.
From that perspective, a bra-ket is like a phase-matching filter. It's configured to detect a specific pattern of coherence. A keter represents stored coherence, a stable pattern of motion.
Okay.
And the act of measurement, the whole Syrah thing, is like a gainy rephase. It projects the stored coherence onto the filter, amplifying the match and giving you a definite result. It maps really nicely onto the operational meaning.
Very elegant. What else was in the tool belt?
Another key tool was the delta function. Now, technically, it's not a function in the strict mathematical sense.
Right. It's infinitely tall and infinitely narrow.
Exactly. Zero width, but with a total area of 1. It's the perfect sync impulse. You can't physically create one, obviously.
An idealization.
Precisely. Mathematically, it represents the limit, the asymptote of tight alignment. It's incredibly useful for picking out a single precise value or state. Fundamental in signal processing, quantum field theory, everywhere.
Okay, and then there's his insight about electromagnetism, that it just appears.
Ah, yes. Gauge coupling. This is incredibly profound. Dirac showed that if you just insist that the laws of physics describing a charged particle, like an electron, shouldn't change if you tweak its quantum phase locally.
Meaning change it differently at different points in space and time.
Right. If you demand that kind of phase symmetry, then electromagnetism isn't something you have to add in separately. It falls out as a necessary consequence to maintain that symmetry.
How does that work?
You have to replace the standard way of measuring change, the ordinary derivative, with something called a covariant derivative. This new derivative automatically includes a term that adjusts for those local phase shifts. And guess what? That extra term is the electromagnetic field, represented by the potential A.
So the field is required just to keep the phase consistent everywhere.
Basically, yes. In the motion theory view, you can think of that gauge field A as the connection that keeps distant phase comparisons meaningful. It tells you how to properly compare the ticks of quantum clocks far apart.
And force.
Force, like the electromagnetic force, is simply the curvature of that connection. It's how much that phase comparison rule twists and turns across spacetime. It's a radically different and much more elegant way to think about forces.
It all comes back to symmetry and consistency, which leads us right into Dirac's core philosophy, doesn't it? This belief in beauty.
Absolutely. It's central to understanding him. He famously believed that the right equation is the most beautiful one consistent with known symmetry.
And that experiment would just have to catch up eventually.
Exactly. He was willing to bet on it. He gambled on the economy of invariance, the idea that nature prefers theories with the fewest arbitrary parts, the most inherent, beautiful structure.
It's almost a leap of faith, trusting aesthetics so deeply in physics. Why should the universe care if an equation is beautiful?
Well, that's the million-dollar question, isn't it? But it connects directly to that motion theory idea. Beauty equals max coherence per assumption.
Say more about that. Max coherence per assumption.
The idea is that the universe doesn't just happen to be beautiful, its beauty is functional. It favors descriptions, laws that allow motion to sustain itself coherently with the minimum amount of sort of arbitrary rules or contrivance.
So simplicity and elegance aren't just nice-to-haves, they're efficient.
In a deep sense, yes. When you express the dynamics through an invariance statement saying this relationship must hold true under these transformations, then consistent structures just naturally crystallize out of that requirement. The beauty is the efficiency and self-consistency.
Okay, but even Dirac had things that bothered him, right? Despite QED's incredible success, he wasn't entirely happy.
That's true. He was one of the founders of quantum electrodynamics, QED, but he became quite uneasy with a crucial technique used in it called renormalization.
What's that, roughly?
Well, QED calculations initially produced infinite answers for things like an electron's mass or charge. Renormalization is a mathematical procedure to sort of sweep those infinities under the rug by redefining the bare parameters of the theory.
And it works spectacularly well.
Well, unbelievably well. Schwinger, Feynman, Tominaga figured out how to do it consistently. QED predicts things like the anomalous magnetic moment of the electron to like 10 decimal places. It's arguably the most successful theory we have.
But Dirac called it ugly.
He did. He felt it was mathematically artificial, a trick, not a fundamental solution. He wanted a deeper cut, a theory where these infinities just didn't appear in the first place.
His quest for beauty again.
Exactly. His discomfort, though, it wasn't just complaining, it was a valuable pointer, suggesting something was still missing in our understanding.
How does motion theory view renormalization?
It sees it as a kind of local retuning of the alignment connection at different scales. It works, it gets the right answers, but the fact that you need to do it suggests there's a missing global coherence constraint, something that should fix these parameters naturally across all scales.
So Dirac's unease points towards a future theory.
We think so. A theory where renormalization happens by construction, because the underlying symmetries are so complete that these parameters emerge finite and correct from the start. Addressing Dirac's aesthetic objection could lead to deeper physics.
Okay, another fascinating detour Dirac took was magnetic monopoles.
Yes. The hypothetical particle with just a north pole or just a south pole, not both like regular magnets.
Right. And Dirac showed something amazing. If even one such particle exists anywhere in the universe,
then electric charge must be quantized. It must come in discrete packets, like the electron's charge. It can't just be any arbitrary value.
that connection seems bizarre. A hypothetical particle dictating a known fundamental property of electricity.
It's profound. It's a topological statement. It connects the global structure of the electromagnetic field, which would be altered by a monopole, to a local property, quantized charge.
How does that work in the motion theory picture?
Well, if monopoles exist, it means the fundamental alignment field of the universe has twists in it, non-trivial loops. And if you imagine moving a charged particle around one of these loops, its quantum phase has to come back to where it started. It must close to preserve coherence.
Okay.
That closure requirement mathematically forces the charge to come in integer multiples of some fundamental unit. So monopoles are like defects in the alignment field, and just the possibility of their existence locks the ledger for electric charge everywhere.
Have we found any?
No free magnetic monopoles have ever been definitively detected, despite many searches. But interestingly, things that behave like monopoles, synthetic monopoles, have been created and observed in weird quantum states of matter, like Bose-Einstein condensates.
So the idea still resonates.
Absolutely. And the charge quantization argument, that endures as a lighthouse. It's a powerful piece of theoretical physics.
Okay, let's touch on something really strange from the Dirac equation itself. Zitterbewegung.
Ah, the trembling motion? Yeah, that's a weird one.
Dirac noticed his own equation predicted that a free electron, even in empty space, should be undergoing this incredibly rapid, tiny, jittery motion.
It comes from interference between the positive and negative energy solutions that are both inherent in his relativistic equation.
Is it real? Can we see it?
For a single free electron, the amplitude is way too small and the frequency way too high to observe directly. But it's not just a mathematical ghost. Scientists have managed to simulate Zitterbewegung using trapped ions, engineering systems that obey similar equations, and perhaps more significantly, effects analogous to Zitterbewegung have been seen in electrons in graphene, where, as we said, they behave relativistically. So it seems to be a real feature of relativistic quantum mechanics.
What's the motion theory take on this trembling?
It's seen as the beat frequency between two permitted coherence branches. The particle's underlying motion loop is, in a sense, trying to satisfy both the positive and negative energy alignment. Exactly.
Yeah.
When you perform a measurement, you essentially select one branch, say, the positive energy one, and that damps the beat, stopping the observable tremble. It highlights the dynamic nature of quantum states.
Wild. Okay, one last area. Putting Dirac into the context of gravity, of curved spacetime.
Right, trying to make the Dirac equation work not just in flat space, but in the curved space-time of Einstein's general relativity.
That sounds complicated.
It is. You need some extra mathematical machinery, concepts like a vierbein or tetrad, basically a local set of axes at each point, and something called the spin connection.
That being connection.
Yeah. It essentially tells you how the orientation of a spinor, the mathematical object describing particles like electrons, changes as it moves through curved spacetime. It turns out that spacetime curvature becomes a phase twist tax on spinors.
So gravity literally twists the quantum phase.
In a way, yes. The path a particle takes through curved space affects its internal quantum state.
And the motion theory view on that.
In that framework, gravity itself is seen as the convergence of sync density regions where the background alignment field is thicker, drawing things together. The spin connection then becomes the necessary bookkeeping of how that alignment twists along the paths of least action, the geodesics.
So it tracks the twists needed to stay coherent in curved space.
Exactly. Things like frame dragging, where a spinning black hole literally drags spacetime around with it, can be interpreted as phase precession induced by rotating convergence. It provides a potentially unifying language.
Okay, wow. We've covered a huge amount of ground. Thinking about Dirac's whole approach, what are the big, lasting lessons? The things anyone trying to understand reality deeply, maybe even using motion theory, should take away.
Yeah, there are definitely some core principles, maybe 4 big ones.
Let's hear them.
First, start with symmetry. Don't just try to explain observations after the fact. Demand fundamental invariances first, and let the necessary structure, the ontology, emerge from the mathematics.
Let symmetry lead. Okay.
Second, linear if you can. Linearity is mathematically clean, it preserves probabilities, it's the natural language of superposition and coherence. Stick with it if possible.
Keep it simple and consistent. Makes sense.
Third, predict, don't just paint. A good theory shouldn't just describe what's known. It should make bold, risky predictions, like antimatter. It should make debt-bearing bets on reality.
Be falsifiable, be bold. Got it.
And fourth, be allergic to knobs. Too many free parameters, things you have to adjust by hand to fit data, that often signals a lack of deep understanding. Aim for theories where parameters emerge naturally from the core principles.
Minimize the adjustable parts.
Yeah.
Okay, those are powerful guidelines. So how does motion theory stack up against those? What does it explicitly keep from Dirac, and what does it change or drop?
good question. Motion theory definitely keeps the focus on linear symmetry first dynamics. That's absolutely central. It keeps the idea of gauge fields as connections that maintain phase coherence.
Right.
It absolutely keeps antimatter as a necessary partner arising from fundamental orientation or phase, and it keeps bracket notation as the clean operational grammar for quantum states.
So it embraces a lot of the core structure. What does it drop or recast?
Well, it drops the literal Dirac C picture, replacing it with the more abstract idea of orientation flip or phase reversal. It aims to recast forces not as fundamental primitives, but as emerging from the curvature of the alignment connection.
Getting rid of force is a basic thing.
Trying to, yes. And critically, it views renormalization not as a fix, but as a signpost. It aims for a structure with built-in scale alignment, hoping to resolve Dirac's original discomfort with those infinities by avoiding them altogether.
Addressing the ugliness. Okay, so if you, our listener, had to take away just a few key phrases about Dirac from this deep dive, what would they be?
Some mental postcards. Maybe? Dirac, write the symmetry and let reality fill the blanks.
I like that.
Or perhaps, antimatter is phase, not just philosophy. It's a structural necessity.
Good one, maybe?
Gauge is how motion remembers orientation at a distance.
Captures that connection idea.
And the big one, connecting to his core belief. Beauty is compressed coherence.
Nice. Those capture it well.
You know, Dirac's legacy is just immense because he showed maybe more clearly than anyone before that equations aren't just descriptions after the fact. They can be causes. They reveal the underlying constraints.
Rules of the game.
Exactly. When you respect the deep invariances, the deep symmetries, you find that motion doesn't have that many ways it can be coherent and self-consistent. And those few allowed ways, those become the particles, the interactions, the universe we see.
It's constrained by its own need for consistency.
Precisely. And that's the aspiration of something like motion theory. Not just to admire Dirac's beautiful equation, but to try and match that level of insight, to write down the fundamental laws of alignment, of structured motion so cleanly.
That things like spin, charge, even the measurement process itself.
Just fall out as necessities, not as things we add in, not as metaphors, but as direct consequences of the core principles.
A high bar, he said.
An incredibly high bar. But Dirac showed the path. Fewer knobs, stricter symmetry, bolder predictions. So here's a final thought for you to ponder. If everything is motion, as motion theory proposes, then maybe the specific universe we find ourselves in is the one where Dirac's elegant equation represents the most economical, the most beautifully coherent way for motion to stay in tune with itself while respecting the fundamental speed limit of light. Deep sortus clarity. Think about that deep link, elegance, symmetry, and the very substance of reality.